So thank you, Renata. Thank you all for the hospitality. It's my pleasure to give you the final presentation for the Work Package 10, JRA2. As you know, this JRA is organized in this way. So we have 3 tasks. The first one is dedicated to target, the second one is focused on ion sources, whereas the third one is completely dedicated to isotope separation techniques. These are the institutions involved in the 3 tasks, but I would like to highlight some extra contributions coming from SCK and INFN for task 2, and an extra work, a huge work done by KU11 and by Professor Kokolios in the context of task 3. So the outline, this is the outline of the presentation. It reflects perfectly the organization of the work package, with some additional general notes at the end related on deliverables and publications. So I would like to start with targets for direct production. And in particular, I would like to illustrate the work done by my colleagues at INFN. So they use the high energy vibrational powder plating technique to produce thin titanium, enriched titanium targets for the cross-section measurements. In particular, the irradiation tests for these targets were done at Aronax, and they were capable to measure the cross-section of scandium 47. They also work with the spark plasma sintering technology for the production of the targets. They produce several target materials, and at the end of in these months, they are concluding the development of the zinc oxide target and of the gadolinium oxide targets for the production of copper 67 and terbium 155, respectively. I would like to go on describing the important work research activities done by the Aronax group, in particular for the production of terbium 155. They are deeply involved in the research activities for both thin and thick target productions. In particular, I would like to highlight the work they did on molecular plating technology. In particular, they deposited natural gadolinium on a titanium substrate, and this is the result showed by these 2 figures. Then in second step, they made cross-section measurements, and here you can see in red the measured points that are in good agreement with the different references that we found in literature. At this point, I would like to move to the description of the activities done by Daniel in the context of high-power targetry. In particular, they developed an high-power rotating bismuth target for the production of astatine 211, irradiating the target with high-energy alpha beams. They developed the target, they designed the target and manufactured it during the first period of PRISMAP. Then in 2023, they made the first preliminary test, and in September 2024, they made the most important test, the main test, I would say. They irradiated 3 targets with alpha beams at high energy, 7 MeV per nucleon, and they produced 1 gigabecquerel for each target. 2 of them were dispatched to Aronax for the post-processing phase. I would say that this test was successful, but with an unexpected detection of gaseous astatine after the run. So now the Aronax group, the Daniel group, is working to fix this problem, and they are ready to deliver astatine 211 to Cicerone for extraction and labeling in the context of this approved and financed project. I would like to move at this point from direct targets to isol targets. I would like to highlight this research activity that was done at INFN in the first part of PRISMAP. We started producing titanium carbide discs for the production of scandium-47 and scandium-44 through the ISO technique. This is the first standard material we produce. It's a titanium carbide characterized by low density and was completely characterized at high temperature. In particular, here you can see the measurement of the emissivity and the thermal conductivity we made. This is the reference material for our space target architecture. So we have actually spaced disks. But in the second part of PRISMAP, we wanted to improve the characteristics of this material. And in particular, we wanted to improve the release properties that are very important for scandium beam production. And we wanted also to improve the capability to dissipate heat by thermal radiation from this material. And so we moved forward describing and defining a new material with a higher specific surface area. In particular, we adopted at the beginning the direct heat writing technology. That is an additive manufacturing technology. This is the result we obtained. The material is satisfactory, but not enough in the sense that the geometrical accuracy was not perfect, I would say. So we moved to this other technology developed in collaboration with the University of Padova and the ISO Next initiative financed by INFN. And so with the digital light processing, that is another additive manufacturing technology, we developed these complex structures that are characterized by an extremely high specific surface area. This is the sample as fired, and this is the sample after thermal treatment. So we obtain a completely crack-free samples after thermal treatment, and we register homogeneous shrinkage along the Cartesian axis. The good point is that we can obtain the structure that we want, so it can be deeply optimized for the proton beam that you have, for the primary beam that you have in your facility. And we also verify the possibility to reproduce the same structures with uranium carbide. So this is these are some tests we made at JRC Karlsruhe, and this is the paper that we published together. So last but not least, regarding ISO targets, this is the important contribution given by ISTID. They worked a lot on uranium solid solution with refractory carbides, and in practice with these alloys, they were capable to obtain materials that are capable to work at extremely high temperature, close to 3000 Kelvin. So as you know, this is a very important aspect since high temperature is very important for the diffusion and fusion processes that are typical, extremely important in ISO targetry. At this point, I'd like to make a very brief outlook and for task one. So we can surely say that we consolidated the collaboration activities on direct targets between INFN and Darmstadt. We have also an important group of institutes that can offer a great support in terms of know-how for ISO targets, and we have Ganit that is very active in high power targeting. So I would say we have a strong and consolidated network for the future of PRISMA Plus proposal and developments. At this point, I would like to move to task two. Task two is dedicated to ion sources, and in particular, I would like to start with the developments in hot cavity ion source technology. As you know, hot cavity ion sources are constructed in this way. So we have a very hot cavity, and that is connected to a transfer line that is in turn communicating with the production target. That is most of the time here, located here. So this ion source was designed in the context of ISO facility, so it works very well with low density, low intensities, and this in general characterized by very high efficiency values. You can produce ions using both surface and laser ionization. In particular, for laser ionization, you can tune different lasers in order to ionize selectively a specific element, the specific element that you want to extract. And this is working well for ISO facilities, but for medical radionuclide production, you typically have a pre-irradiated sample or target that is evaporated, ionized, and mass separated. So this causes a very high ion load in proximity of the hot cavity region that in some cases can suppress completely the ionization effect of the laser. So you can see the effect in normal conditions. Here you can see the laser extracted ions at the extraction region, in the region of the hot cavity, in the region of the transfer line. When you increase the ion load, this curve becomes flat, as you can see in this graph. So to address this problem, colleagues from CERN defined 3 different experimental tests. In the first one, they imposed an axial magnetic field in proximity of the hot cavity. And the second one, they injected inert gas argon in the ion source to reduce the mean free path of the ion, so to improve the ion survival. Unfortunately, these 2 tests did not satisfy the expectations, but the third one registered some improvements for the laser ionization process. During this test, they threaded the internal surface of the hot cavity. So in this way, they increased the surface area for thermionic emission of electrons, and this improved. It seems that this improved the ion confinement, so the performance of the source. These are preliminary results and need to be consolidated, but all details of these tests can be found in deliverable 10.3. Another important aspect for hot cavity ion sources is the temperature profile. You need to have an extremely high temperature in both hot cavity and transfer line, close to 2,200 Celsius degrees. And a good example of thermal design is surely constituted by the isolate mirror hot cavity ion source. In the first part of PRISMAP, they developed the mechanical design, they studied thermally this object, and they produced the first prototype for the testing at high temperature. Recently, in 2025, they characterized the source with stable ions, with stable ion beams. And in particular, they measured the laser ionization efficiency for gallium and obtain results that are similar to other benchmarks, like the SPES one. And this is the SPES hot cavity ion source. It is correct. It was designed some years ago, and it was optimized in terms of temperature profile, and it is characterized by this characteristic alignment setup for the hot cavity. We had the opportunity to test it at CERN offline a couple of years ago. We measured time structures. We made some measurements with alternating laser on and laser off conditions. We measured laser ionization efficiency. So we completed a strong and important set of tests and that were published in these 2 papers. And at this point, we can surely say that and underline that the Medicis Isolde, the isolate mirror, and the SPES hot cavity ion sources were designed and developed in parallel, independently by different groups. But the good thing is that they were characterized at the same test bench, and we registered complete sharing of results among these groups. And I would say this is an important remark. This context is ideal for the improvement of the performance of these objects. I would like to mention a couple of slides regarding favorite ion sources, and in particular, dedicated R&D effort at INFN demonstrated the feasibility of producing favorite ion source components. Here you can see the cathode, this is the main component of the source, via laser powder bed fusion. That is an additive manufacturing technology that is capable to give you components in a single block instead of welding together smaller pieces. And it is not trivial, since we are talking about refractory metals, so this is very difficult to manage this process. But we are capable to prove that it is effective, and we produced an ion source, a favorite ion source with this component. The performance are comparable to standard counterparts, and the tests were done, the ionization efficiency tests were done at the ISOLDE offline. So in practice, we have this technology available for the future developments, and in practice, with this technology, we can produce the shapes that we want, that we prefer for this kind of sources. Another important activity with favorite ion sources that is important to mention is surely the activity that we made a couple of years ago at CERN for the production of thermal beams using molecular beam technologies. In particular, we injected fluorine in the target ion source unit, obtaining molecular terbium beams, and we demonstrated that we can produce these beams at temperature levels that are sensibly lower with respect to the standard ones. I would like to, at this point, I would like to go to these important developments that are related to carbon, to ion sources for carbon-11 production. As you know, the positive emitter carbon-11 is used for particle-based radiation therapy. In particular, it's important to verify the three-dimensional location of the Bragg peak. And the carbon-11 is produced irradiating with protons at boron nitride target. The amount of carbon-11 we obtain is not huge, so we need to adopt efficient ion sources for the ionization process. We tested with the Med Austrian group and the CERN group 3 different ion sources, so the favorite VADIS MK7, the super nanogram ECR source, and the COMI source. All these solutions presented strengths and weaknesses. At the end of the day, the super nanogram ion source was indicated as the best option, considering the full chain. So the total efficiency 0.6 is higher than the other two. We have a low ion source efficiency, but in the case of super nanogram source, the charge splitter is not required. It is required for the other two. So the super nanogram represent the best option for further developments, even if some work is needed for the production of carbon-11 in quantities that are sufficient for treatments. Also, in the case of ion sources, we put together very strong research groups, and we constructed an important basis for the future PRISMAP Plus developments. And last but not least, task 3 is dedicated to laser-enhanced isotopically selected condensation technology for the enrichment of calcium and titanium radionuclides. We started at the beginning of PRISMAP with density functional theory calculations for the identification of the most appropriate precursor for this enrichment technology. We identified the commercially available calcium hexafluoroacetoacetonate, and in the second part of PRISMAP, we the gas phase infrared spectroscopy was done, and to investigate the vibrational modes of this compound. And the measure spectrum agreed well with the DFT calculations previously defined. So also for these tests, we can surely say that they were successful tests. They demonstrated the feasibility of this technology, and a similar approach may be followed also for the enrichment of titanium. Regarding the deliverables, we completed all the deliverables in due time. So we have 2 deliverables for each task. And this is the list of publications, of the main publications that we have in the context of Work Package 10. And I would like to thank you for your attention. And of course, if you have questions, I will be glad to answer. Thank you.